Welcome to the fourth and final DYNAMO presentation in our webinar series. This series is being hosted by the Climate Variability and Predictability Program of NOAA's Climate Program Office. If you're having any your audio, please send a question to Amrit and he'll help you get set up with the audio. There's on your right-hand screen or in your GoToWebinar control panel, there should be a phone number to call in or a button to click to use your mic and speakers on your computer. So again, thanks for joining us. These webinars are intended to showcase research funded by the Climate Variability and Predictability Program that was conducted as part of the DYNAMO campaign. And that campaign ran from the fall of 2011 in the spring, of 2011 to the spring of 2012. That was in the Indian Ocean. The campaign, consisting of in-situ observations from moorings, aircraft, land, and shipboard sensors, part of a larger research program involving data analysis, modeling, and forecast improvement components that are ongoing today. The overall goal of DYNAMO is to develop a better understanding of Madden-Julian Oscillation and its importance on the global climate system, especially on the season interannual. Advances in our understanding of the MJO can provide predictions climate and weather models, allowing them to provide better forecasts and projections in the future. In pursuit of this goal, DYNAMO tried to capture the structure and evolution of cloud populations, air-sea interactions, and larger-scale environmental interactions. This series of presentations will share the latest results from these projects and will allow the PIs to discuss the importance of their work, outcomes, and lessons learned to date with a broader scientific community. As you listen to the presentations, if you have any questions you'd like to ask, please type the question into the question box, which is on the control panel for the GoToWebinar. You can enter these questions at any time, and we will address them at the end of the presentation. Please include your name and who you are addressing the question to. Because of the number of people listening to this presentation, all of your lines will be muted, which is why we use the question box instead. So, again, thank you for joining us. Our first speaker today is Toshi Shinoda. His talk is entitled Upper Ocean Processes in the Indian Ocean Associated with MJO. He's an associate professor of atmospheric science at Texas A&M in Corpus Christi, where his work focuses on climate dynamics, atmosphere-ocean interactions, physical oceanography. Toshi, thanks for joining us. At this time, we will turn the controls over to you. And I think they're all set.
Thank you. This project mostly focuses on the oceanic processes associated with the MJO. And here I selected 4 specific topics. And the first one, large-scale ocean variability and impact on Indonesian through-flow and diurnal cycle and the variability of thermocline ridge. So the first topic is large-scale ocean variability. So as Sandy introduced, the DYNAMO field campaign took place in the fall and winter 2011, and a lot of data have been collected from both atmosphere and ocean. And upper ocean measurements mostly occurred in this central Indian Ocean area just south of the equator, and a lot of high-quality data have been collected. However, MJO is a large-scale phenomenon, so we would like to know how the large-scale ocean circulation and upper ocean variability look like surrounding in this region. So we first look at the large-scale upper ocean variations surrounding this intensive array based on the satellite data and the ocean general circulation model experiments. And just review the MJO events during the DYNAMO field campaign. And this is a longitude and a time plot of the OLR near the equator. You see these 3 MJO events propagated eastward in the Indian Ocean. And in association with this these events, especially November and December event, you have a strong westerly wind anomaly near the equator. And so the important thing for this oceanic process is that there is no clear suppressed phase between second and the third events. So the relatively strong wind lasted more than one month. And in the October event, there are some anomalies, but in the Central Indian Ocean, anomalies are not that strong here. So the major ocean response occurs during November and December event. And we look at the satellite data. These are the data we used. WindSat for the surface winds and TRIM for the precipitation. Abyssal data for sea surface height, and some high resolution Reynolds analysis for sea surface temperature, and Oscar surface current, and the sea surface salinity of the new satellite called Aquarius. And note that these Oscar current and Aquarius accuracy is still uncertain. So we use the global hybrid coordinate ocean model, HICOM, and horizontal resolution is 1/12/25 and 1/12, and the surface forcing is no gaps. And this is an example of sea surface salinity. You see this low salinity Bay of Bengal and high salinity in the Arabian Sea. And first we look at the surface winds associated with the MJO. And the buoy data, buoy measures the surface wind in a DYNAMO area. And you can see in late December and late November and late December, you see the strong westerly wind. And this, the wind set well captures the strong westerly wind in November and also December here. So we can look at the spatial pattern of this westerly wind event. And this is the November, late November event, and this is the late December event. And this shading is the wind speed. And you can see the different spatial pattern in the two events. And in the November event, you see this the strong westerlies are seen in the entire equatorial Indian Ocean. And so this is associated with the Arabian Sea cyclonic circulation. On the other hand, December event, you see strong winds. It's mostly found in the eastern part, and that is associated with a strong cyclonic circulation in the Bay of Bengal. And this is a large-scale sea surface temperature variation. This is a time series of sea surface temperature at the DYNAMO area, 80.5 east, 1.5 south. And this green line is observation, and you see this large variation, intra-season variation associated with the MJO. And this blue line is a high-resolution Reynolds analysis, and the two curves are quite similar. And in late December, you see this cooling occurs after the onset of MJO, because there is no clear suppressed phase, and the cooling occurs until the end of December to early January. So this is large cooling, and we can look at the spatial pattern by Reynolds SST, and this is the difference between this period, early January, and onset time in late November. And you can see the significant cooling is seen in almost the entire Indian Ocean south of north of 10 south, and this could impact the atmospheric convection. And this is a large-scale salinity variation, and we compared this Aquarius sea surface salinity with the observation around the DYNAMO area. So this is a buoy data. The green one is a buoy data, and Aquarius is blue one. And you can see this intraseasonal variation of sea surface salinity, and it increases near the equator, 1 point south, and so the Aquarius capture this variation. In the 4 south, it's constant in time, and 8 south, you have a decrease of the salinity. And so we can look at the large-scale pattern from the Aquarius measurement, and the shading is a salinity, and the arrow is Oscar surface current. And you can see this the high salinity. This is a November 1st to 15 average. So here you have an increase of a salinity near the equator, and you can see this high salinity from the Arabian Sea advected and causes the increase of the salinity here. On the other hand, here, the 8 south, you have this the relatively fresh water coming from the east and advected to the 8 south. So that explains decrease of the salinity. And for south, it is constant. That is between the eastward current and the westward current, and horizontal gradient is very small, so it is constant. So these two data sets are consistent and explain these variations. And this is a zonal current and sea surface height, longitude time plot. And you see this strong zonal current is generated after the late November event. And so this is a late December map of sea surface height, the shading, and currents. And you see the strong equatorial jet accumulate these upper waters near the eastern boundary. So in this kind of situation, you can the Rossby wave can generate from the eastern boundaries. We look at the time series after those events. So this is a longitude time plot of a satellite-derived sea surface height, or up to the early March at 4 south. So you see this accumulation of upper ocean water that's propagated as a reflected Rossby waves, and the reach around 60 east. So this is a region so-called thermocline ridge, Seychelles-Chagos thermocline ridge, where the main mean thermocline depth is very shallow. That means it is the sea surface temperature is very sensitive to the small change of the thermocline depth. So if you have this kind of a Rossby wave, it could impact the sea surface temperature here. And we look at the global high cone, and it can simulate the these Rossby waves well. And so we can look at the thermocline depth variation. This is a 20 degrees C isotherm depth. And you can see the large deepening, about more than 20 meters, occurs in thermocline rich region. And this is a late February to March thermocline depth, 20 degrees C isotherm depth anomaly. You can see the deeper thermocline here. And this is a sea surface temperature anomaly associated with this thermocline depth. And you can see the significant sea surface temperature warming occurs in the thermocline rich region. So that could generate the atmospheric convection. So this is consistent with the recent hypothesis by Weber et al. 2010, right before the DYNAMO experiments. So in this hypothesis, ocean dynamics play an important role for the subsequent MJO generation. So the MJO generate these Kelvin waves, and then propagate eastward, and the reflected Rossby wave propagates westward, and the thermocline depth gets shallow in the western part, and it affects the sea surface temperature, and affect the atmospheric convection and generate subsequent MJO. And if you look at after these 3 MJO events, and the Rossby wave propagated westward slowly to the east, and in March it reached around 60 east. And here the atmospheric convection is generated and organized and propagated as MJO to the Western Pacific. So this scenario is consistent with the DYNAMO case. And the next topic is impact on Indonesian true flow. So the first, I'd like to explain the seasonal variation of the Indonesian true flow before I talked about the DYNAMO case. And this is observation from Gordon et al. So Indonesian true flow carries Pacific water to the Indian Ocean through this area of complex topography. And about 80% of the true flow passed through this strait called a narrow strait called Makassar Strait. So there's an observational project called Instant Observation, and this is a result of the observation of the mooring around here. This is a transport through the Makassar Strait, and you can see the clear seasonal cycle, semi-annual cycle, and the southward transport is reduced twice in a year, the May and October and November. So the model can reproduce this semi-annual cycle, and analysis indicates that this reduction is caused by a Burki jet on the equator in the Indian Ocean, and that propagates along the coast of Sumatra and Java and influence the Makassar Strait transport. On the other hand, rapid recovery from the December to March is primarily caused by Pacific annual Rossby waves. So the question is, how do strong MJO events during DYNAMO impact the Indonesian true flow? So during December, you have a strong jet generated, and you see the accumulation of the upper ocean water here. So this is a global HICOM experiment. You see this the large-scale zonal currents near the equator, and this is so-called the Yoshida jet that lasted more than 1 month. And if you look at the Makassar Strait meridional velocity, in September, October, you have a strong southward currents in upper ocean, and that decreases with time. And in a previous slide, we showed that from mid-December to February, it recovers. But however, in this case, it continued to decrease until February. So this is the upper ocean transport. So this is caused by the coastal Kelvin wave propagating from the equator. So this shading is the velocity component along this line all the way to the Makassar Strait. And here it's a Makassar Strait northward anomalous current. That means a reduction of the Indonesian true flow transport, and that can be traced back all the way to the equatorial Indian Ocean. This is a strong Yoshida jet generated by the MJO events during the DYNAMO period. And the next topic is the diurnal cycle. We increase the vertical resolution in the upper 10 meter. So the resolution is now 1 meter to generate the realistic diurnal warming. And this is the observation in the DYNAMO area, the red one. And you can see this, the high cone can generate the realistic large diurnal warming. So we can examine the impact of a diurnal cycle on intraseasonal variability. So this is our previous work based on the Toga core experiment and the one-dimensional ocean modeling. And the one-dimensional ocean model was forced with the first hourly forcing and also daily mean forcing, but the daily mean values are the same. So you can see the significant difference between these two, and the red one includes the diurnal cycle solar radiation, and the suppressed phase of the MJO, it's warmer, and the active phase diurnal cycle of solar radiation is weak because of cloudy. So as a result, you see the larger amplitude of intraseasonal variability. So we did the same thing for the three-dimensional ocean general circulation model. So by increasing the higher the resolution of the upper 10 meter. And we can look at the different location in many MJO events. And this is a composite of the many MJO events. For example, this is the central Indian Ocean here. And you see the similar difference is seen in the diurnal case and the non-diurnal case. This difference is quite significant, consistent with the 1D model. And the next, the final topic is thermocline rich variability. Previously already explained the Seychelles Chagos thermocline ridge, where the main thermocline depth is very shallow, and it's important reason because sea surface temperature is very sensitive to the main thermocline depth variation there. And we found that the model is able to reproduce at least the thermocline depth variation in the Indian Ocean, so we can look at the longer time series. So here we examine the impact of thermocline ridge interlinear variation on the intraseasonal SST variation. So the thermocline ridge varies interlinearly because of the ENSO and IOD. For example, IOD years, the Rossby waves impacts the thermocline ridge. And the question is, how does ocean interlinear variability impacts the intraseasonal SST and in the thermocline ridge region? So we did additional experiments. In these experiments, no interlinear variation of surface forcing fields are included. So the other timescale variations are included, but not the interlinear variation. So we can look at the intraseasonal SST in two cases. Original experiments include all timescales, and another one is no interlinear variation. So this is the difference of the intraseasonal variability of SST around here. So you can see the significant difference is mostly seen in the eastern part of the thermocline ridge region, and it enhances the intraseasonal variation. And this is, we look at each year of the difference, and the red one is no interlinear variation, blue one is an interlinear variation. So if you look at the thermocline depth, it's sometimes shallower, sometimes deeper. Here we define the deeper case is a weak thermocline ridge year, and the shallower case a strong thermocline ridge year. And in a shallower case, strong case, you can see the enhancement of the intraseasonal SST, and the deeper case and the weakening of the intraseasonal SST. And but this is not the symmetric the strong ear case, you have the larger difference. This is the intraseasonal SST. And the weak ear case, the difference is smaller. So the overall effect is similar to stronger ear case. And also you can see the thermocline depth difference. In the stronger ear, you can see the larger difference than the weaker ear case. And finally, we look at the thermocline structure in a weak thermocline ridge case and the strong thermocline ridge case. This is the average between 20 south and 4 south. And you can see the overall, it's shallower, but the location of the ridge moves towards the central Indian Ocean, so that causes the eastern part of the ridge has a larger difference here. That causes the major impact in the eastern part of the thermocline ridge region. So this is a summary. Variety of upper ocean processes associated with the MJO that influence SST are identified by the analysis of ocean general circulation model experiments and the satellite observations. And these include equatorial jet, diurnal cycle, variation of thermocline ridge, and the remote ocean variability, such as Indonesian through flow. And of course, further analysis are needed, especially how this SST changes feedback onto the atmosphere. Thank you.
Great, Toshi. Thank you so much for that presentation. We did get a question come in during it, and if anyone has any other questions, please put them in the chat box or the question box, and I'll read them out. So our first question for you is from Renshi. The question is the salinity budget in the Indian Ocean mostly advection dominated?
So it is still an ongoing study. And advection certainly important by calculating the salinity advection from the Arabian Sea high salinity water and the south of the equatorial region and the fresh water advecting westward. However, there is entrainment effect that cannot be negligible. For example, the equatorial jet influences the mixing of high salinity water from the deeper area. And that is before the MJO event. And once MJO event happens, the high precipitation, heavy precipitation occurs. And after late November, the freshening of the mixed layer occurs. That is due to the heavy precipitation associated with the MJO. So at the onset of the MJO, the surface heavy precipitation seems to be dominant, and it is larger than the horizontal advection.
Okay, great. There's one more question. Renshi says thank you, is one that came through. A second one, another question is, what is the dominant baroclinic mode of the Kelvin wave modeled in Mascar Strait during MJO? And this is from, I can't, this is too small. Kendra Pujana from OSU, Oregon State.
Oh, okay. I believe this is the first baroclinic mode, but at least in the model. And yeah, I'm not sure how important the second baroclinic mode. So we haven't looked at the detail of the second baroclinic mode yet.
Okay, thanks. All right, thank you again. We're going to move on to our next presenter. Up next is Eric Maloney describing MJO dynamics and model biases in the DYNAMO hindcasts. He is currently an associate professor of atmospheric science at Colorado State University, and his research interests include tropical meteorology, hurricanes, ocean-atmosphere interactions, climate dynamics, and climate modeling. Eric is currently on sabbatical in Australia, so his presentation is pre-recorded. Since he's not in the room with us today, please send any questions that you may have about his work to his email address, which is emaloney@atmos.coloradostate.edu. You can also email me to get that address if you need it. At this point, we'll play the presentation, which is recorded in advance. It's about 25 minutes to 30 minutes. After that, I'll do a wrap-up, and I'll turn it over to Amaris to go ahead and start.
Listed here, including the Whitney MJO.
Can you increase the volume?
And we'd also like to acknowledge our funding agencies, particularly NOAA ESS program, NSF on the large-scale dynamics, and NASA Cygnus. So this plot here features some of our past aquaplanet results, and much of the diagnostic work that I'm going to present in this talk is going to view the MJO through the prism of a moisture mode. And so moisture mode is a class of disturbances where understanding the regulation of moisture is critical for understanding destabilization and propagation of the MJO. And so this shows one example from a 2010 paper. Let me highlight one aspect here. And so this upper right plot shows the horizontal advection anomalies from a composite MJO life cycle in this model. And you can see here positive horizontal advection occurring off to the east of MJO precipitation and very strong drying ensuing to the west of MJO convection. And we showed in this model that horizontal advection dominates the moisture tendency and is responsible for eastward propagation of the MJO in this model. A broader body of research around the same time that we wrote this paper suggests more generally that the MJO is a moisture mode which is destabilized by cloud evaporation and wind evaporation feedbacks and is propagated eastward through horizontal advection. So we've used this hypothesis to explore the MJO moistening process in a variety of data sets. And so this plot here shows some results that I obtained with one of my postdocs in 2011, and this is published in JGR, showing the critical role of horizontal advection in the ERA-I data set for regulating the moisture budget in the Indian Ocean DYNAMO Webinar. And on the left-hand plot here, it shows a partitioning of the zonal advection part of the moistetic energy budget, and it highlights the critical role of zonal wind anomalies acting on the mean moisture gradient in the Indian Ocean for both moistening, out here from phases 0 to 180, and drying, phases 180 to 360 here, for regulating the moisture budget of the MJO of the Indian Ocean. So in regions of anomalous easterly flow, the troposphere moistens, and in the subsequent to MJO convection, when you have anomalous westerly flow, there's a very strong drying, and advection down the mean moisture gradient appears to be a very important process in this. So some recent work by Emily Riley, who's a postdoc in my group, using an extended record from the Rama array in the Indian Ocean, has suggested an important role for surface flux feedbacks in destabilizing the MJO. Emily has shown that late heat flux anomalies are about 10 to 15% of precipitation anomalies during interseasonal events in the Indian Ocean. This shows one example here from the 90-degree east Rama buoy. Previous studies suggest that convection discharges moisture at a rate of about 20% of precipitation. And so the fact that latent heat flux anomalies are contributing about 10 to 15% of precipitation anomalies in the Indian Ocean suggests that surface flux feedbacks play an important role in helping to destabilize the MJO. And of course you need other things to make up that difference. You also likely need cloud radiative feedbacks in order to help explain the destabilization as well. But it looks like surface flux feedbacks are a very, very important part of that. So as co-chair of the WGNI MJO task force, we've been contributing to a gas project where hindcast experiments are generated during MJO events to understand MJO physics and to understand model bias. And this shows, some examples here of the things that we've been doing. We've been conducting short 2-day physics errors experiments where we save data at every time step so that we can get a detailed process understanding of what's going on in the model. Then we have daily and weekly forecast errors that can be surmised from short-range hindcasts, 20 days. We also have long climate simulations. So one of the things that this experiment has been doing has been hindcast experiments of the MJO. Initially, the first part of this project looked at MJO events during the Yahtzee period, but more recently, orders have gone out to the modeling centers across the globe to also do hindcasts for the DYNAMO period, specifically with a focus on the November DYNAMO event. And so this is going to be a very nice database that we can use to not only get a process-oriented understanding of the MJO, but also hopefully help to diagnose some of the model biases that we see in this region. So this experiment has actually helped to motivate a lot of the results that I'm actually going to show next year. So what I'm going to show now are some explorations of MJO dynamics and also forecast error in a series of DYNAMO hindcasts from several different models. So one model that I'm going to show here is the NCAR-CAM5. And we're going to use a few different configurations of the NCAR-CAM5 with different values of entrainment used in the dilute cape calculation. Changing the entrainment rate is a very common method to increase MJO activity in models. And I'm going to show that that's indeed what happens, but it comes at a relatively significant cost. I'm also going to more briefly show some hindcast experiments from the SP-CAM. And I'm also, at the end, going to show some results, some initial results from hindcast experiments using the Ocean Atmosphere Land Model, or OLAM. In all of these experiments, we're going to use ECMWF operational analyses as initial conditions to start the hindcasts. And we're going to launch simulations that are 20 days long, starting every 5th day through the period October 1st through December 15th, 2011. So this is going to span much of the observation period of the Sydney DYNAMO experiment. So this shows some results from the CAM5. And so as I mentioned, a common method of improving convective moisture sensitivity and MJO skill in models is to increase the entrainment rate. And I show equatorial average precipitation from TRIM on the left here, and then the 1-week forecast from 3 different versions of CAM5. We have a version of CAM5 here on the far right that's a low entrainment version, and a version of CAM5 here, second from the left, that's relatively high entrainment. So one thing that you can see here is that as entrainment rate increases, you get a better and better representation of MJO convection at 1-week lead time versus this low entrainment rate model where there's actually very little evidence of coherent MJO activity by 1 week into the forecast. So we can also assess hindcast skill using some of the methods that have been derived by Gottschalk et al. 2010 and others. So this plot here shows some examples of MJO forecast skill using bivariate correlations on the left here and root mean squared errors on the right here. And these measures of forecast skill are compared relative to observed RMMs, observed real-time multivariate MJO indices that are derived by you or intended. And you can see here that there's a significantly larger MJO forecast skill both in the bivariate correlation measure and also the RMS error for the high entrainment runs. So they diverge pretty strongly and pretty soon away from the low entrainment runs, just a few days into the forecast. And if we had extended this out to 20 to 25 days on the x-axis here, you would see that the high entrainment runs have MJO hindcast skill out to about 20 to 25 days if you use standard measures of bivariate correlation of 0.5. So the high entrainment runs are competitive with the forecast skill that we see in the best models today in the field. But not all is good here, and so we've shown a improvement of MJO hindcast skill in the models. But what I'm going to show now is that the CAM5 simulation with high entrainment might be producing good MJO skill for the wrong reasons. So I'm going to demonstrate this using the vertically integrated moist static energy budget. So for weak temperature gradient conditions that are characteristic of the tropics on interseasonal timescales, the moist static energy budget essentially becomes a moisture budget, and that's what this first equation here shows. So there's a moisture tendency on the left, horizontal and vertical advection on the right, and then also moist static energy sources including latent heat flux, sensible heat flux, and radiation. A very nice feature of using the moist static energy budget to diagnose processes associated with the MJO is that when you do so, vertical advection implicitly accounts for the cancellation of precipitation and vertical moisture advection. And so this cancellation becomes actually exact when you add vertical advection and radiation together. So it gets around the problem of in the moisture budget of having to separately diagnose vertical advection of moisture and precipitation and sort of sort out the cause and effects. And so this equation succinctly combines those two things together and accounts for their cancellation. So this plot here shows a few of the moist static energy budget terms for era I on the top and the high entrainment model on the bottom. And so the first column shows horizontal advection, second column shows vertical advection, and then the third column shows sources of moist static energy, including latent heat flux, sensible heat flux, and radiation. One thing that you could immediately see here is in the horizontal advection term, both in era I and the high entrainment model, you see an enhancement of horizontal advective drying subsequent to MJO precipitation events. And so this is consistent with our 2010-2011 results, and it's also consistent with some of the things that people are finding with the DYNAMO array. The middle panel here is the vertical moist static energy advection, and you can see here, and I think this isn't that difficult to see with your eye, that there are some significant differences between era I and the high entrainment version of the CAM5. So you can see here that predominantly CAM5 tends to import moist static energy into the column by vertical advection, whereas era I tends to be maybe a somewhat weak export of moist static energy into the column. So fundamentally, vertical advection is doing something different in the CAM5 compared to era I in this context. You also see here that the era I has relatively strong variations in moist static energy sources, such as radiation anomalies, latent heat flux anomalies, whereas these anomalies are still apparent in the Zahn-McFarland scheme, the CAM5, but they're not quite as strong. So this is actually reinforced in this next plot here that I showed. This plot here basically shows the same thing as I did in the previous panel, but now the analysis is centered over the DYNAMO array and displayed in a slightly different form. And so what both of these plots here show on the x-axis are moist static energy anomalies. And you could think about these as being proportional to the strength of convection. So stronger convection is given by higher values of moist static energy anomalies. And then the strength of column radiative heating is shown on the left axis, the y-axis of the left plot. So this is column radiative heating. Then the strength of vertical moist static energy advection is shown on the y-axis of the right plot. So one thing that you could see, first looking at the column radiative heating, is that long-wave cooling does not seem to be strongly suppressed enough in the CAM model when you have convection occurring for large values of moist static energy anomalies. Things seem to be okay when there's suppressed convection in clear sky conditions, but there's not enough of a suppression of long-wave heating, of long-wave cooling to space when you have active convection occurring in the model. So this seems to suggest that long-wave radiative feedbacks in the model are not strong enough. An alternate interpretation of this plot may be that precipitation doesn't respond properly when you do have a long-wave heating anomaly that's imposed in the model. So that's an alternate interpretation of this. The right-hand plot suggests that models with high entrainment tend to import moist static energy into the column too strongly relative to era I, for a large range of convective conditions, including convective conditions with relatively active convection occurring. So this also suggests some problem in the energy balance terms in the model. So our interpretation of these results is that vertical advection is erroneously importing moist static energy into the column in the high entrainment models to compensate for radiative feedbacks that are too weak. And so what this accomplishes is that this helps to maintain moisture anomalies erroneously in order to produce a good MJO in the models. And it suggests possibly that these models with high entrainment are getting a good MJO simulation for the wrong reasons. So, what are the reasons for these biases and what are the consequences? One thing that we've diagnosed is that the higher entrainment simulations of CAM5 tend to have a more bottom-heavy vertical velocity and heating profile relative to era I. And this bottom-heavy nature of the vertical velocity and heating profiles is, creating differences in vertical moist static energy advection relative to era I, so that the high entrainment models, due to the very bottom-heavy nature of vertical velocity profiles, are importing too much moist static energy into the column when convection occurs. So these moist static energy biases, we think, might provide some clues as to why improving the MJO in climate models using certain techniques to degrade the mean state. Kim et al. 2011 showed this nicely. Many of the models with good MJOs in that study tended to have common biases, such as very strong and excessive precipitation biases in the Northwest Pacific during boreal summer. And we think that some of these biases may be due to the incorrect partitioning of energy budget terms in these models when you pump up things like entrainment. Let me briefly talk about here some of the SP-CAM results that we've been obtaining so far. We have a whole paper on these results in itself, based on SP-CAM, and so I would urge you to contact me if you have any questions, and I could lead you to more details on these results, but I'm just going to go through them relatively briefly here. So what the top plot shows are essentially the 1-week forecasts, and now I'm showing U850 in era I, and so this is sort of the ground truth that we're comparing to. SP-CAM in the middle here, and a relatively high entrainment version of CAM5 on the right. And so you can see immediately right here that the SP-CAM produces extremely strong MJO events when initialized 1 week before the forecast time that we show here. So the combination of this very strong MJO activity that you see here and also some drift in the SPCAM mean state that projects onto the RMMs. Tends to produce some very interesting results when you look at the skill scores. One thing that you see is that SPCAM produces outstanding skill scores when you look at anomaly correlations. It shows skill scores that are as good or better than many of the models the best models that we have out in the field today for looking at MJO activity. But the SPCAM, when you look at the root mean squared error skill scores relative to observed RMMs, does actually relatively poorly. And it's due to, again, this very strong MJO activity and also the climate drift that we see in SPCAM that projects onto the RMMs of Wheeler and Hendon. And this plot down here on the lower right shows an example of the drift in U850. And you can see U850 becomes anomalously easterly here, just past the date line, and anomalously westerly in the climate drift in the Western Pacific. And this projects very strongly onto one of the RMM indices. And what is the reason for the very strong MJO activity in SPCAM? One thing that we find, and this is a comparison of Q1 between SPCAM and ERA I as a function of convective activity. And so convective activity is now is defined somewhat differently. It's defined on the basis of dry static energy advection, but the story is the same. On the right of this plot, you have suppressed convection. To the left of this plot, you have enhanced convection. So as you go left, stronger convection occurs. And one thing that you could see from this plot is that SPCAM tends to have a very bottom-heavy Q1 profile. And associated with a very bottom-heavy Q1 profile, you also tend to have a very bottom-heavy vertical velocity profile. And so this causes excessive moist static energy import into the column by vertical advection. And it actually makes it too easy for convection to maintain moist static energy or moisture anomalies in the model. So it makes it much too easy for the MJO to be destabilized in this model with such a very bottom-heavy profile. And so that's the reason for some of the very strong MJO activity that we actually see with SPCAM in the last plot. Okay, so the last model that I'll talk about here that we've been doing some hindcasts for is the OLAM model, the Ocean Atmosphere Land Model, created as a growth of the RAMS model that was maintained here at CSU, but it's been taken a step further by Wacko and Abasar and Wacko and Abasar 2011. And the OLAM model technology that actually allows local mesh refinements to be done in places like the Indian Ocean. And so this is one configuration that we've been looking at in this figure here, with a relatively coarse global mesh with a refinement that's centered over the DYNAMO array here in the Indian Ocean. And what we've been doing over the past few months is that we've been testing various dependencies of the configuration of OLAM, including various parameterizations, various nudging techniques, and also various initialization techniques. So eventually what we're going to do here is we're going to have an inner domain, maybe with a few degrees of mesh refinement that allows the domain over the MJO DYNAMO SINDI array here to be cloud system resolving. So our ultimate goal here is to put a 1 kilometer domain right over the DYNAMO array, but retain a relatively coarse global mesh outside of the Indian Ocean. So let me just show you some initial results from some of the experiments that we've been doing with OLAM. The experiments so far with OLAM, have been relatively promising so far. So the experiments do show that the OLAM can produce dynamo MJO events with some degree of fidelity. And so this plot here shows the 1-week precipitation forecasts from OLAM, clearly showing both the October and November dynamo MJO events. And we could also look at the UA50 simulation. So you could also clearly see these two, the first two dynamo MJO events here in lower tropospheric winds. So it looks like OLAM has been having some success in capturing the essence of the first two MJO events with some fidelity. Another example here is providing by the moist static energy budget anomalies. And you could clearly see this very strong November dynamo event in OLAM, and also evidence of the end of the October event here in OLAM, and with suppressed periods in between. So this is promising. I guess I wouldn't break out the Cheetos just quite yet, since many of the runs that I've been showing do have a bit stronger degree of nudging than I would like, and so we probably want to help refine some of these nudging strategies before we get into a more detailed process-oriented diagnosis of the model. But at least from what we've seen so far, there seems to be some very promising aspects of the OLAM simulations to this point. Okay, so let me wrap up here with a summary and a few closing thoughts. So we presented here some multiple modeling and observational results that have used MJO moisture mode theory to help understand the basic dynamics of the MJO. We've also presented some process-oriented diagnostics that we've applied to MJO hindcasts that provide some clues as to why good MJO simulations often tend to have degraded mean states. We've seen some fundamental differences in the moist static energy budgets between models with good MJO and observations, which tends us to believe that there's an incorrect partitioning of energy budget terms in some of these good MJO models, which might explain their poor mean state simulations. We've also shown some initial hindcast experiments with OLAM that are very promising in their simulations of dynamo MJO events, with some caveats that I also alluded to before. So some issues and overall lessons and future work ideas. One lesson that we've gained is that sometimes simple fixes to improve MJO simulations may produce good MJO activity for the wrong reasons. And so my discussion of energy budget errors and incorrect partitioning is related to this point. So maybe the lesson here is that in addition to more realistic treatments of entrainment, more emphasis might be placed on other aspects of convection parameterization, such as mesoscale organization and its impacts, microphysical schemes, which might affect radiative feedbacks, and also more attention might be placed on simulation of the continuum of cloud populations and their reflection and vertical heating profiles in order to produce reliable simulations of the MJO. One very nice example of this sort of a study that hints at that is that of Shakira 2014. And Shakira 2014 highlights, for example, the fundamental role of cumulus congestus during the MJO enhanced phase for helping to destabilize the MJO in a version of the model that he used. And so, again, there may be more aspects than just simply entrainment rate that we might want to pay attention to when thinking about this problem. I also think that more process-oriented diagnosis of models is needed to assess whether or not models are producing correct MJO simulations for the right reasons. I think a very useful tool that we're going to be able to use in this endeavor is the OLAM model. And the OLAM model, particularly with its refined mesh capabilities, and cloud system resolving capability over the Dynamo array is going to be an extremely useful tool in this endeavor, and is going to allow us to dig quite a bit more deeply into some of the processes related to both MJO destabilization and propagation over the Indian Ocean. So we might be able to test, for example, some of the dependencies that Shakira suggests on cumulus congestus and its role in destabilizing the MJO. And we might also be able to test, impacts of wind evaporation feedbacks, and also the effect of ambient shear in the environment on convective organization in this model. So we're very excited to apply OM model to problems like that. And with that, I thank you for your attention, and I think that I'll take any questions that you might have via email afterwards. So thank you very much.
Thanks, everyone. That was Eric Maloney. And as I mentioned earlier, please send any questions that you may have about his work to his email address, which is emaloney@atmos.colorado.state, or I'm sorry, colostate.edu. I'd like to just do a quick wrap-up, which is we would like to thank you all for joining us for this set of presentations in our series of the Dynamo Field Campaign webinars. This is the final presentation of the series. However, we will be starting up a new series in the fall. The focus of those webinars in the fall will be the CVP-funded projects that are looking at AMOC. We'll send out a broadcast email to all of you for that series once the details are finalized and dates are set. I'd also like to thank both Hunter Jones and Amaris here at CPO for their hard work preparing these presenters and setting up the technology for this webinar. I'd also like to thank today's presenters for taking the time to share their work with us. This concludes our series. Please feel free to email me or Hunter Jones or any of the presenters if you have any additional questions or need information. We hope that you have a great day. Thanks for joining us.